So in the previous classes, we studied about the one-stage adiabatic buffer in the conventional system. There we calculated the minimum total energy for one stage. So as we know that the one-stage adiabatic buffer in the conventional system consists of one transmission gator and one clamp NMOS actually. The necessity of this NMOS is you need to discharge the capacity energy. For that purpose only we are having this clamp NMOS. Next, so there was a one small correction in the previous class. Here we given input. This is the output is Y. Previously I have written here Y bar actually. No, this is not the Y bar. This is the VA, the input. That is stepwise the time variant signal we are going to give here the VA. Slowly we are going to increase in the ramp here. That is the input here. So as you know that when x is equal to 1, so example, when the x is equal to 1, then this capacitor will be on, then the transistor transmission gates also will be on, then automatically what will happen, slowly when you increase this, so it will charge your capacitor, but by the time even this also it is on, so it may get discharged. There will be some problem also will be there. So that is why so we need to go for some other technique also. So here we analyzed with the stages like when the Vin is equal to VDD. That is what, as I mentioned here, the input will be VD signal. So what we said was all your input energy will be dissipated. Then we assumed here the input capacitance means the node capacitance. So all the total input capacitance of the input will be directly proportional to the gate capacitance, because here you can see this input, the X will be connected to gate signal. So there will be a capacitor gate signal. As you know that when you take any NMOS transistor, you might have studied so many capacitance will be there. That is the junction capacitance, and all around the terminals will have a capacitor. Say example, the capacitance between gate and drain, the capacitance between gate and source, the capacitance between source and bulk, then the capacitance between bulk and drain. So that only we can call it as the capacitance between drain and source. Then the capacitance between gate and substrate. So these are the so many various parasitic capacitance will be available over there. So here we are considering there is no parasitic effects but capacitance. Then we calculated the total energy. So in that we said finally we calculated the in the previously the on resistance, that is R on. So again finally we calculated the E total in terms of VDD and if in terms of VTH also, in which way we need, so we can do. That is about the one stage actually. Now what we'll do, let us go for second stage. Okay, so to stage, so adiabatic buffer in conventional system. Okay, so two-stage adiabatic buffer conventional system in the sense, as you know that the one single stage, the adiabatic buffer will be represented as as I mentioned here, so previously we mentioned. Now we are going to do two stage. So that is the one stage. So the one stage is driving the another stage. If it is that is the way, then we may have two inputs and two outputs we are going to do. Okay, so how it is in the sense of previously we done in this way. For one stage, so we given the input here, right, VA, then the output we are taken as Y over there, then here it will be X. Okay, so I will draw the diagram. So So now let me draw the cascading of two stages. This will be a first VA, then ground, then this is VB, ground. So here we have a capacitance, that is CL here. Then here also we are having the capacitance, that is CL. Then we have like this. So this figure is Cascade Adiabatic Amplifier. Here a smaller adiabatic amplifier, that is I can say a smaller adiabatic amplifier is used to drive the input signals of the final stage. This is what we have shown in the figure here. So now let us consider here. Previously for single stage we took as Cn is a gate capacitance. So now here what will let us consider the capacitance like let's we consider the Cn1 and the Cn2. Previously we took only Cn, right? So here because two stages. So this will be the gate capacitance. Gate capacitance of the NMOS device at the first and second stage. First and the second amplifier you can say. Next I'll say alpha Cn2. You can remember the previous we written alpha Cn. Here the alpha Cn2 is nothing but it's an input capacitance of the second. Input capacitance of the second amplifier. Now what we'll do, just let us alert the off of the total charging. Off of the total charging time to each stage. Okay, so let us allocate the half of the total charging time for it. So in the sense complete charge for both the sides, like just let us take it 50% of first stage and the 50% for the second stage. So like that let us take. So what you need to do, already we know that some two equations. Let us recall that equation already we know, that is one equation is the Cn. The Cn is nothing but 2, that is psi alpha tau 1 by 2 into 1 by m minus 2, then this will be a root into Cn. This is your Cn. Then what about the En? That is input energy. The input energy is nothing but alpha Cn into VDD square. Yes. So this is starting body input energy. The Cn is nothing but gate capacitance. So now from this what we do? Let us take the total. What is the total now? Actually the total is nothing but, if you want to say, it will be like E in. Already we said that will be like a E in 1 first stage and E in 2 the second stage. Then will be finally we have E load. So this E in only we are splitting it to E1 and E2 actually. So now where the E in 1, what is the E in 1? Let us write where the E in 1 is nothing but alpha Cn1 VDD square. Then E in 2 is alpha Cn2 VDD square. Now what about the E load actually? Here you remember here in this E load actually the previous E load, this is we know, or I will write the previous E load. What is the E load actually? Even this also will take it from the previous. Okay, what is E load? The E load is nothing but 2 sine by 2 sine into tau 1 by t into 1 by m minus 2 into, we remember that previous CL square by Cn into VDD. See here, as we know that the CL is nothing but the final output stage, right? This one. CL is nothing but the final output stage. The Cn is nothing but the input capacity of the previous stage. Now you tell me this EL will be the first stage, second stage. The output will be CL, but the input is Cn2. That is not Cn. I hope you might have got it. Correct. So what about for first stage now load? See, because the first stage output only is driving the second stage. If I consider the first stage output is nothing but your E load, if I consider, then that will be what? The ratio of the Cn2 by Cn1. So that is nothing but Cn2 square by Cn square. So we need to write like this. The load will have like that. So the one stage and the second stage. So let us write in that way for the first stage. This is E load for first stage. So what is the E load for first stage actually? It is nothing but alpha into, right, because the first stage here E in, so here we written for first stage will be like alpha into next will be there. So first stage will be alpha into 2 times of sine tau 1 by t 1 by m minus 2 1 by m minus 2. Then here what you get? Cn2 square, right, divided by Cn1 into VDD square. Similarly for E load for the second stage. E load in this is completely, if I take completely, here we are taking half of your right? Completely in the sense what will happen? If I write E total, E in 1 plus E load plus E into plus E load. Actually E load of first stage and E load of second stage. But the last only we are taking as complete last E load will take. So just we are considering this. Okay. For the second stage what will happen? Like it's driving, so there will not be any alpha will not come. So it will like 2 sine tau 1 by t into 1 by m minus 2. What is the output? Output is CL actually, right? CL square divided by the input is Cn2. That is output capacity, the input capacity into VDD square. So I think now you got it. Now what we need to do? We need to substitute the things over there for the first and second. So let me write down E total. Now let us write E total. E total will be is equal to alpha Cn1 VDD square plus the output of first stage, because here alpha we took. We are writing completely, right? Don't write completely because here itself E in 1 alpha is there. Alpha into that. So E into will be like this. So I took generalized I'm writing. So will be like alpha is nothing but the scaling factor. Alpha Cn1 is nothing but the input capacitance of that is gate capacitance of the first stage. That is input stage, not first stage, the input stage. VDD square plus 2 into tau 1 by t 1 by m minus 2. So here we are saying this alpha is right. I am going to take this alpha into so alpha square, right? Alpha square Cn square by Cn square by C n1 into VDD square. So you may think like Cn2 800, this is Cn2 square by Cn square VDD square plus again 2 times of psi tau 1 by t 1 by m minus 2 then Cl square by Cn2 VDD square. Now let us simplify this expression. So we'll get alpha Cn1 into VDD square. Then this will become 2 plus 2, 4 actually. 4 psi tau 1 by t into 1 by m minus 2 into alpha square Cn2 square by Cn1 plus Cn square by Cn2 into VDD square. You can consider the expression as in this way. Now you can say when both the Cn1 and Cn2 are free variable. The Cn1 is a free variable for second stage. Okay, so now what we'll do, let us find the minimum total energy dissipation is the minimum total energy dissipation is now we have to write in terms of VDD and in terms of VTH we have to write. So let us say E total minimum. E total minimum. This is in terms of in terms of VDD. Just writing E total minimum will be is equal to, will get us 8 times of alpha into psi tau 1 by t into 1 by m minus 2 the whole power 3 by 4 into CL into VDD square. Because here we are considering something like the Cn1 is equal to Cn2 is equal to Cn we are taking. So in the above expression you consider the Cn1 because both are free variable. When both are free variable, just we can do in this way. So we'll get the expression as like this. Next in terms of VTH. So in terms of VTH, E total minimum is equal to 8 m square, because in the previously for the first stage we wrote in terms of VDD and in terms of VTH also. Similarly you have to write even here also alpha into tau n divided by t into 1 by m minus 2 to power 3 by 4 into CL into VTH square. Now here we can make some observation, that is from the first stage from one stage to the next stage, one stage to the next stage or one stage to the two stage. To the two stage, the minimum power dissipation it will like energy scaling will improve, energy scaling which will improves from 1 by root to t, that is half, right, at t to the power minus 1 by t to 1 by t the cubic root of t. So now you can see when I go for one stage or the one stage you are going to 1 by root t. So what is our ultimate aim? Actually we need to increase this t, right? This was going to increase slowly in the ramp when you increase, automatically your power dissipation will get reduced. But when you go for the two stages, what happened? This is root t, that is t to the power 1 by 2. What happened? This one root t of the cubic root. When it is goes cubic root, automatically what will happen? Still minimum power dissipation. So the energy scaling will be improved in this. So it has shown that for the cascading of n stages, when it shown that as cascading of n stages, such amplifier the energy scaling or the energy dissipation scales are, these are the scaling factors, okay, scales are, that is that E total minimum will be is equal to E total minimum approximately will be is equal to t square the power minus n minus 1. This is what actually we will get. This is about the two stage actually. Now let us see if it is the fully adiabatic, if it is. fully adiabatic system. Fully adiabatic system. Okay, so now what you have to do, the sense previously, just conventionally, the driven control segments will cause a sublinear dependence of energy on time. So truly, it like the true the true 1 by t scaling. Here the scaling is 1 by t. The 1 by 2 scaling can be achieved only if the system uses adiabatic charging throughout. Adiabatic charging throughout. Okay. So now what you need to do, we need to assume, let us assume a cascade management. Okay. Cascade. So let us assume cascade arrangement with the input of the first amplifier adiabatically driven. Adiabatically driven its next its device dimension is fixed. Device dimension is fixed, and the charging time allows charging time t actually. Charging time t allowable for each amplifier. So for this also the system is fully adiabatic system. If the system is complete fully adiabatic system, then so we need to assume these things. So from this what we can do, let us calculate the dissipation. The dissipation for driving the load and the input at the second stage. Input at the second stage amplifier is the minimum total energy dissipation, that is E total minimum is equal to 2 psi into tau n by t. This is already been known, right? Mi minus 2 into alpha square Cn2 square divided by Cn1 plus Cl square divided by Cn square into UDD square. The minimum, total minimum is power dissipation for driving the load and the input of the second stage. So now from this you can say the Cn2, that is nothing but the gate capacitance of the second stage actually. So this will minimize the dissipation. Minimizes the dissipation. Minimize the dissipation as independent of m actually. It's independent of m, then under tau n by t. the Cn2, because you can see here it doesn't have the Cn2, Cf terms actually, because the second term it will minimize the dissipation and independent of m and tau by t. So the dissipation is linear in t. So the dissipation is linear in t. So from this we can add the optimal capacitance gate capacitance for second stage, that is Cn2 optimal, right, will be written as Cl square into Cn1 divided by 2 the whole power 1 by 3. So from this I can write the final, that is the total energy E total will be is equal to 2 psi tau 1 by t into 1 by m minus 2, then cubic root, right, cubic root of 2. So cubic root of 2 plus 1 divided by the cubic root of 4 into Cl divided by Cn1 the whole power 1 by 3 into Cl into VDD square. This is the total energy for the fully adiabatic system. Now you can see here things like Cn2 is omitted here actually. So only thing is very important, the Cn1, because it is intermediate, so the output also will be there finally. This is nothing but fully adiabatic system. Even we can compare with the conventional buffer actually, just like you can compare the dissipations of the adiabatic buffer with the conventional one. So because for different speeds and different voltage swings. So if you want to drive the input and the load of a conventional buffer with mobility scaled devices, giving a same total of input capacitance for transmission gate, so that will cause a dissipation. So even we need to find out. So even you can find with the respect to VDD, or you can find out with respect to VTH also. So that is we are not going to discuss anyway here. So this is about your the adiabatic amplification stage. So now next to what you have to do, so with the help of this adiabatic amplifier, the amplification circuit, so we need to design, or we need to construct a adiabatic logic gate. So the next will be adiabatic logic gate or logic gates. So here what you have to do, we have to construct, or we have to take examples how you constructed the gates with the conventional CMOS for logic gates, for combination circuits as well as for sequential circuits. Similarly, we need to do here also. So for that, what we need to do, we need to know the general structure of the static CMOS circuit as well as the adiabatic circuit. For adiabatic circuit diagram also we need to know. So very important thing. For that, what I will do, let me go for the circuit first. I will draw the circuit here. This will be the circuit as static CMOS circuit, because we need to know the difference. Static CMOS circuit. So here I will draw the adiabatic circuit. Okay, so let us draw that. Static CMOS, as we know that this will be your PMOS network. So I am going to take as a F function, then this I am going to take as a F bar, or you can take another, right? A simple static CMOS circuits in the sense a normal PMOS and NMOS, right? So now here this will be your input, then this I will take it as output, then here we'll have the output, then this will be your capacitance, and here we'll have the current, then here we'll have connect the VDD, fixed VDD will connect, very important power supply, right? This will be your out. So as we know that this will be your PMOS network, that is pull up network. This is your pull down network, that is your NMOS. This will be your PMOS. In CMOS circuit, this is actually even you can go for like this is static CMOS circuits, okay. Now for the adiabatic, how it will be in the sense, simply same F, then F bar, then let us connect this will be your, see, this is will be your input, this will be your output, then here we will have the capacitance, here also we will have the capacitance, then this input we connect to the source, but here the source is not the fixed source. Fixed source we will use the random signal, right? This is nothing but your what is we can say, ramp signal kind of, we can say, right? So this is what is slowly step variation, step input, you can say, you have to do. This will be your adiabatic circuit, this will be a static circuit. Okay, how it will convert, or we need to know. So for that, what we will do, let us show the procedure. What are the procedures we have to do? Okay, the procedures to convert static CMOS to NMOS. Procedure to convert static CMOS to adiabatic. First, so what you need to do first, you have to start with the static CMOS gate. Okay, start with the static CMOS gate. The adiabatic logic gate for the same Boolean function can be realized. So you have to start. So first step number 1, let's say. What you have to do, the step number 1, that replace each pull up NMOS network and pull down PMOS network. See, actually, even here I drawn like this, right? You can see, sorry. Here, F, this is F bar. F bar means the sense this will be your PMOS, correct? This will be your F. F in the sense it is NMOS. You can see for always will connect the NMOS here. You connected the input. Just the example we took like this, okay? So that is why here written replace the each pull up NMOS network and pull down PMOS network there. Or but generally if I want to say in static CMOS circuit with transmission gate, if I say replace each pull up NMOS network and pull down PMOS network of a static CMOS circuit with the transmission gates. First, that is TG. First step is what you have to do. You have to replace the pull up network and pull down network with the transmission gate. First step. Simple, just to make it in this way. Step number 2. Step 2. So you have to use the expanded pull up network SPUN, okay, pull up network to drive the true load capacitance. True load capacitance. That is just step 2 you have to do. So step 2 is what? You have to use the expanded pull up network. Expanded pull up network to drive the true output capacitance. Next, step 3. Use the expanded pull down network, that is PDN. Pull down network to drive the complementary output. Complementary output load capacitance. Load capacitance. That is your step number 3. Next, the last step, that is step number 4. What you have to do then? You have to replace the VDD, that is your fixed power supply. VDD by a pulsed power supply. Because in the adiabatic logic circuit, we are going to use pulsed power supply only, that is VA. So these are the steps we need to follow. So from this we can say how the adiabatic circuits where both the networks are used to charge and discharge the load capacitance adiabatically. So what we need to do now, with the help of this, we need to realize the realization of gates. Realization of gates. Gate using adiabatic logic. So the first one is the adiabatic realization of the realization of AND or NOT gate, okay, of AND or NAND gate. The realization of AND or NAND gate using adiabatic. We know that for NAND AND gate using static CMOS circuit, how to draw. That we know very clearly, right? So now what you need to, you have to go for the AND or NAND gate. So for NAND gate, first what you have to do in the sense, like as you know that they have to draw the static schema, so it will be better always. Let us start with the static actually. First you draw the static CMOS NAND gate. So it is a two input you can consider. Okay, so further what I will do, so top is bottom, top will be your PMOS. The PMOS NAND gate will be parallel in structure. So PMOS parallel in structure. Then NMOS series in structure. Versus this will be your VDD, correct? So just you remember that circuit VDD in the sense here you can think in this way. Okay, the circuit just I will put like this. VDD, then we connected here. Then this I will consider as X, this I will take it as Y. This I will consider as X, and this I will consider as Y. So you see, this will be not X, it's supposed to be X bar, right? Actually it's a X bar. This is supposed to be input is Y bar actually. X bar and Y bar, this is X and Y. Then this will be your out. The out is nothing but Y. So now here what you have to do, you have to convert this to adiabatic logic circuit. You have to convert now. So we can first we have to rearrange this. Instead of doing that, we have to rearrange. In the sense, the PMOS and the NMOS, you can rearrange X and X bar as well as the Y and Y bar. You can rearrange it. So now what you need to do, we need to convert this to adiabatic logic circuit. So what we can do, first as we mentioned here, we need to replace the pull-up network and the pulled-out network with the transmission gate. So now you remember, so how many transmission gates are required here totally? So here we are having a T1, this is T2, this is T3, then T4. So replace the T1, T2, T3, T4 with transmission gate. So if I convert or replace with the transmission gate, what will happen? Here only the transistors are only 4 transistors are required. But when I convert this into adiabatic logic circuit, each and everything will be replaced with a transmission gate. So if I am replacing the transmission gate, the number of the transistor will be double now. It is like around how much? It is like I can say 8 transistors. So now what you have to do, we have to do. So now you can see this is the output portion. Now we need to convert that. Okay, this is the center portion's output. No? Okay. So now what you are going to do in the sense, we are going to take in the output here. The input is X, right? So let us draw the circuit. If you replace, just I will go with the construction how it is, then later we will convert to adiabatic logic. So this, you see, this circuit is done. What you do to make better, rotate this circuit by 90 degree. Now just to think in that way, how it will be. Rotate by 90 degree or rotate by 90 degree in counterclockwise, anti-clockwise. Example, because it will be very easy for you. Okay. So rotate this diagram by anti-clockwise by 90 degree. The meaning is left rotate. Left rotate by 19 degree. For our convenient purpose only I do it. Okay, one left rotate we do. This circuit will become as, how it will be the circuit? Just let me draw that. I hope you got it right. This will be your X bar. Just this is X only. You consider this is X only. Okay, just example. No need X bar also. You can X and Y only input, just to mention that better. So it will be very easy for us to take it. Even this also X and Y. Then this will be your VDD, right? See here, VDD. Okay, so this will be connected this here. Okay, so now you can see this, or what I can do in the sense, I can say like this will be your just I'll put like this. This will be your, when you are going for realization, that is F and F bar, as we mentioned, right? Just we did like this. So now what we need to do, we need to again convert, as I mentioned earlier, replace the each and every transistor with the each and every transistor with the transmission gate. So now you can see that. Let me replace it, and I can put that one. First transmission gate. This will be first. This is X. This is X bar. Because you can see here the PMOS I am replacing here. Okay, the input is X. The PMOS X is only. Even I am using here PMOS is X. The NMOS will be Y will come. Next again here one more gate. What about this? So this will be your Y, because see the PMOS is Y. So PMOS is Y, NMOS will become as Y bar actually. So now this is in parallel, right? So now connect this in parallel here. Even this also is connected in parallel. So you connect in parallel. Now the two NMOS transistors. So again what I should do? Transmission gate. But here you can see the NMOS is X and Y, right? So NMOS is X and Y means I will consider this is NMOS X. So then this will be your PMOS. So supposed to be X bar. Then again I can say like this, Y. This is supposed to be Y bar. Then this will be your output where to convert to capacitance. This is something with your F. Then what about the F bar? F bar has to be taken here actually. Okay. Because like kind of two stages, right? So here this will be your F bar. So now where will be the input? The input has to be given where, in the sense this place. This is the input. Pulsed power supply. See now I can say this will be your TG1, this is your TG2, this is TG3, then this will be your TG4. So now you can see will be noted the number of transistors required for realization of the adiabatic circuit will be larger than the static sigma realization of the same function actually. You can see. So here it will be is equivalent. Like this you need to implement for not only for the NAND gate, even for OR gate, even for complex logic. So this realizations and all we will see in the further classes.